Alright, what is up, guys? Welcome back to Intelligence Maxing Day 31. So, in this episode, I'm gonna be working on one of the next projects I have for my machine learning class, and this has to do with data segmentation. So, I actually haven't taken a look at what this is. I'm gonna read through this, kind of make note of what I think is interesting, and then also hopefully get started, write down some code, write down the steps for training and testing. So let's see, let's first import all of our stuff. Okay, I don't know what PIL is, but let's use the download link. You can just download the dataset using this, alright. Okay, it's good. So we have import CV2, import OS. What? CV2. CV2, Python. Open CV. So what is OpenCV? Okay, guess some type of computer vision library. Okay. Computer vision library. Alright. Also, what is image? PIL? What is PIL? Python. Pillow Fork Python imaging library. Open source additional library for Python programming language that adds support for opening, manipulating, and saving many. Okay. What is this called? Python imaging library. Okay. So Python imaging library. Helpful library for manipulating images. Okay. So I know what SciPy is, but I'm not entirely sure what TQDIM is. What is TQDIM? Python. Add progress bars and loops to iterable objects. Interesting. Python progress bar library update. Okay. Python progress bar library. Okay. So these are some of the interesting libraries that we have. We have our data. Alright, let's see what happens here. Plot image. So IM, title, xticks, yticks, CVT. Title of image, list of tick values defaults to nothing. Is the image CV2 image? CV2 images are BGR instead of RGB, default true. So it seems like it swapped the channels, the red and blue channels together. Now, what that actually does to the image, I'm not entirely sure. Okay, so this is RGB values, so 0, 0, 0. I guess void is just black. Building, RGB values. Are these thresholds maybe? So these are thresholds for... Okay, maybe not thresholds, but if we were to identify something as a building, then we just fill in the building as, I think this is probably, so this is the red channel, then we boost up the red in the photo. So does this affects the... does this... I think this change the color of the image based on the label. So if we detect a building, that building will be colored in red. Okay. Background classes is equal to void, grass, and sky. Background colors is equal to empty list, wide, empty list. Okay, so if I in range, so we iterate through name and background classes. Okay, so this loop will add the colors of the background classes to the background colors list. Okay, so I think that's similar to what we had idea. So it'll iterate through this. I guess this list of dictionaries. And then whenever our dictionary represents background, so in this case void, grass, or sky, then we add the color, which is the RGB value, to our background colors list. Okay, so reverse order of channels from BGR to RGB. All right. So I'm not entirely sure what this binary segmentation is. What is binary segmentation? Question mark, exclamation point. For background color and background colors. Okay, so is there, okay, so I'm surprised that the segmentation was able to get it. Plot image 6 sample. Oh, okay, so this is an example. It's not something that's been trained. Binary segmentation, okay, I guess it's true or false. Oh man, this is tough. I'm not entirely sure what this is doing. It's different mass. Okay. Ooh, okay, this is where it gets kind of tough. I'm starting to get lost here in the sauce. There's a lot of stuff here. Okay. Okay, so this seems like it's just creating the image, the testing and the training validation set, also the testing set. I'm not entirely sure how they. So this is kind of confusing. Maybe I'll come back to that, but that's the big idea. X-train. Okay, so we have self X, self Y, self X, self Y. So this is also just setting up the training, validation, and testing data. Okay, so get item. I see. All right. Image transform. Okay, so there's two transformations here, one for the image, one for the mask. Now, I'm not entirely sure what the mask is used for, I'm going to be honest. Maybe it's used for... Okay, so... I'm going to add some comments here. Alright, so we have the training, validation, testing set. So splitting, separating the input data and the ground truth. So these are our labels. Setting up the data loaders and data. Call these data sets and data loaders. Interest is considered foreground, so conv 3x3 relu. Yeah, this is a crazy architecture. Alright. This is kind of insane. Well, let's see. We got 0 views. Let us go. Okay. Got the sun or the light shining right into the camera. Okay. So this is how we use the data loader. Alright. There's an iterator, I guess, on the data loader that we apply. Okay, so seems like, why do we transpose this? I remember I did the same thing for, I think this has to do with the way that, I think the reason why we transpose is the way that PyTorch the underlying code deals with the dimensionality of our data. So I'm gonna add a note here. Why do we transpose? I feel like if we don't add it, what's gonna happen is, let's take a look. Might get some dimensionality error. Okay. Right. So transpose from, we have 3 by 256 by 256 to 256 by 256 by 3. Okay, so that's what this is doing. Same thing here. Okay, so then we take the image and we multiply by 0.5, and then we add 0.5. So why do we multiply by 0.5 and add 0.5? I'm not entirely sure why that is. So the mask, what do we do with the mask? So it seems like the mask is taken from labels, so maybe our label is the mask itself. This might be ground truth. The label. Okay. Alright, so we need to use the iterator, it seems like. Need to use iter next iter data loader to iterate through data sets. Okay. Now we have kind of a baseline of what we need to do, I guess, to interact with the data loader now, so that's helpful. It seems like in order to get the next input or the next label, we have to use next iter data loader in order to do that. And the image that we input into our model is from the inputs, and the mask, which is our label, is received from the labels. And we have to transpose this apparently to 1, 2, 0. I'm not entirely sure how it's represented. It's 3 by 256 by 256. So I'm not entirely sure why it's represented like that in the first place, but we have to transform it to 256, 256, 3. And we do that by transposing. Okay. So this is how we have a test image. 2, 0. Alright. So let's try this again. I think this should work. Alright, now that you are familiar with the dataset, it is time to make a deep neural network to perform these segmentations, where we need to distinguish foreground from background, where the class of interest is considered foreground. Okay, so we're given a little input picture right here. We have to follow the steps here. So we have a convolutional layer 3 by 3. And we have 112 feature maps. Okay. And then we have a max pooling layer. And then we have model is equal to unet, model.CUDA, binary cross entropy loss, optum, model parameters, running rates is 1e -4, challenge submission. Okay, so I think maybe to start, we don't actually have to do all this complex stuff here. We'll just have a single convolutional layer, maybe set up a max pooling layer. So they have this idea of copying, which I'm not entirely sure what that means. I remember our professor was talking about it in class, but I'm going to be honest, I didn't fully understand what he was saying. And also there's this idea of 1-by-1 convolution that is also a bit confusing. So I'm going to have to take a look at what that means. And then you have the up convolution. I'm not entirely sure what this does either. It seems like from this photo, the upward convolution is increasing the number of dimensions. So in this case, we have 128 squared. This one, we have 256 squared. And we're also increasing the number of feature maps. Now, how that actually works under the hood, I'm not entirely sure. Okay. So in this operation, use a conv2d torch.cat and then dot conv transpose 2d and then dot maxpool 2d. You may find it useful to use an dot batch norm 2d as well. Now that you can experiment with different channel sizes, try to start with something smaller than 112, like 16. Okay, so I think what they're referring to here is these feature maps have 112 channels, but realistically it's a bit too big, so probably going to need something smaller, 16 just to start out with. Okay. Follow step function of the optimizer to update the weights of the network. This is done by optim.step. This makes the model deterministic rather than probabilistic. This is ensured by model.eval. As you don't need any gradients during our validation/testing phase. Okay. So let's just take a look at some of these different things here. nn.conv2d, I've never used before. Applies a 2D convolution over an input signal composed of several input planes. Okay, so this is the number of channels in the input, height and weight. This is the number of, I guess you could say, inputs with number of channels on the output. Okay. Okay, so this is a cross-correlation operator. N is a batch size. C denotes the number of channels. H is the height of input. Okay, so I do remember things, I guess, talking about stride and padding in class. Kernel size has to do with the filter itself. So I'm not entirely sure. Is this a single int? Okay. Yeah, this is the size of our filter. We could also have a tuple. Alright. Oops. So first thing we could do, let's try to define a convolutional layer. So conv2d, and then we'll pass in, so there's in channels is equal to, there's going to be 3. Let's do out channels. We'll do 16 for now, and we'll call this input, kernel size. We'll do 3 by 3, and I think default stride is probably 1, padding 0. Alright, we'll just leave it like that for now. So first convolutional stage. So we have convolutional stage. Oh, right. So I think what this is doing, it's taking our I would think this takes our image, our input DEM, whatever this is, whatever DEM stands for. It'll flatten it to a vector, but I would say this vector should be 256 squared times 3 instead of 256 squared itself. So that might be something that's a bit ambiguous. I'm not entirely sure how that should be computed. Okay. So we have another convolutional layer. We'll call this the second convolutional stage. Let's see. Self dot conv1 is equal to self dot conv2 is equal to. So there is no more linear activation. This is a convolution now. And then maybe after the convolution, we'll do some type of activation function. We also have the idea of a max pole. What is com transpose 2D? That's also something I'm not entirely sure. Okay, so this is kind of where it describes it. We have number of batches, height, weight. Alright. So h out is equal to h in minus 1 times stride 0. Okay, so this is getting cut off for some reason. Oh, never mind. Times kernel size minus 1 plus output padding. Plus 1. Output padding. So downsampling, I guess, is reducing the number of dimensions in the data set. So they downsample by taking the com2D. They input the number of channels, which is 16. Wait. So let's say that this is the number of batches, this is the number of channels, this is the height, this is the width. So why is it that if you have a 16 by 16 by wait, what is 16 channels in, 16 channels out, 3 by 3 filter. This will change conv 2D. So why is it that if you have, oh man, input channels, output channels is 16, okay. You have a 3 by 3 filter, so stride of 2, and padding 1. So padding will increase so would this be 52 by 102? Okay, so that means we have a 3 by 3. So this would be 52, this will be 102. 52, I think, is divisible by 3. If we do, is it actually? 3 times 15 is 45. Plus, ooh. Yeah, I don't think it is. Oh, here we go. Okay. So it'll be 1. I see. So it'll be 12 and 12. We add padding of 1, so it'll be, I think, 14. That's weird, actually, because if we take the 12 divided by 2, we get 6. But then we have a padding of 1, so what would happen if... Alright, I'm going to take this, actually. I'm going to do some experimenting here. Alright, let's add something. How do I add code? Alright. Input. Let me downsample. Let's downsample the input. Okay. Ooh, shit. Test.size. Alright, now let's add padding of 0. Okay, so why does this happen then? If you have 12 pixels with 0 padding, how is it that... Alright, let's see. So we have 0, 0, 0, 0, 0, 0. Wait. There's 3 zeros here. 6 zeros. So now we have test, we'll call this height is equal to length of height. So this is 12, alright. So we have a filter that looks at this two, and it looks at these two, and it looks at these two. Oh, it's a 3x3 filter, okay. So if it's a 3x3 filter, look at these three. And then it'll stride over, so 2. Then it'll look at these 3. Okay, then it'll go over. And then look at these 3. Go over here, look at these 3. Go over here, go look at these 3. Okay. I see. So, yeah, this is going to be kind of sneaky because there's a lot of, it seems like there's probably a bit of math involved here trying to figure out what the output dimension is. Okay. So this is the formula that's being used actually. We have the input dimension plus 2 times padding. Okay, that's fair. Minus dilation. I'm not entirely sure what dilation does, so I'll skip that for now. Times kernel size. 0 minus 1. We subtract 1. Divided by stride. Then we add 1. Okay, I'm gonna copy this actually. Let's see if I can paste that into this. Oh shoot. Wait. Oh. Oh shit. Oh man. Okay, it's not really working too well. Not entirely sure what's going on here. Yeah, I'm gonna stand up, go for a walk real quick. Oh shit. Okay. Nice. Alright. Okay, so the inputs, input should be input dim. It will be 256 times 256 times 3. Wait, no, actually, we don't have to flatten everything. So maybe we'll do 128 by 128 by 16. And then go back to 256 by 256 by 16. Okay. So, maybe we need a fully connected stage. So this is going to be 256 by 256 by 3. Yeah. Okay. So we have 3 channels. Out channels is 16. Alright, and then we have kernel size. So we have a stride of 1 and also padding of 0. So what's going to happen then is we'll take the input plus 2, so this is 0, minus dilation times kernel size. So kernel size is going to be a 3 by 3 kernel. I guess it's going to be, so it's 3 minus 2. So it'll be H 128 minus 2 minus 2 minus minus 1 is going to be so it'll be 126 yeah, it's hard to do this in my head. Okay, 128 minus 2 minus 1 plus 1, so that cancels out. So it's just going to be 126 if we do this. Alright, so what we need to do to get to 256. 256 minus 2. Minus 1. 5. Okay, so if we have a padding of 1, so padding is equal to 1, and I think if we add a stride of just 2, then that should give us exactly 128. Okay. Now, how we get to the second part, it's a bit harder. I'm not entirely sure. So, okay, fully connected stage. Second convolutional stage. All right. Yeah. I don't know how, if we were to Hmm. Self. Uh, huh. So once we have, this is gonna be our feature maps. I guess you could call these maybe edges or small little features of a picture. So you could take this. Excuse me. Yeah. Okay. I'm honestly lost at this point. So this is where I need to go to the slides. Also, there's actually one thing I do want to see is what is 1-by-1 correlation or cross convolution? So what is 1-1 convolution? Oh, I am getting a call, so I'm gonna take this in a sec. Hello? 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 Yeah. Hello? 我听不见你。哦，现在听见了。Yeah. Yeah, but no, so. Oh, really? No, 我现在在外面呢。Yeah. 不知道。shit. Okay. I'll start again. Yeah. 下大了。shit. Okay. 我看一下，好像没有。Yeah, 我们可能也会有点鱼，是的。喂，你们那税能自己弄吗？对，因为我已经把我的花了，对，对，Yeah, it's nice. Okay, also 你下星期还想要跟我去吃饭吗？Okay. Yeah. Okay, sounds good. Yeah, DC. 好。Yeah, sounds good. I'll see you. Okay. Yeah, bye.
Ew.
Someone created a family night a little too hard. Maybe they got nervous.
Wait, where's my wallet?
Huh? It's on the cart. Brian has it.
Okay. What's up, guys? Alright, so I think I might move locations real quick. It's a bit cold. Sitting right under the... I think I might be sitting right under air conditioner. Okay, so let's see what this means.
They're like passing documents. If anyone MQBC comes, make sure to talk to us first.
Okay, I'm hearing some crazy sounds.
Right now, by myself, just watching. It's like the same one guy. He looks like you a little bit.
Algún día pues esto quisiera venir así, pero está yo de gerente atrás.
Ay, sí.
Yo la voy a tratar bien.
Ay, yo sé, Jorgito.
Jorgito, no voy a venir ahora. Bueno, venga.
Tranquila, me va a decir. No se
Ah,
preocupe, me va a decir.
so it seems like the basic idea of a 1x1 convolution is all it does is okay, shoot. And in this case, you mapped a 112 channel to a single channel. So I think all it really does is it maps single channel, I guess multiple channels to a single channel. So I think at the end we could add a one by one convolution. Output. So inputs 256 by 256 by 3 to the inputs 256 128 by 128 by 16, and then the output will then be I think oh wait, we might need some type of upsampling thing to increase. So I'm gonna should be maybe 256 by 256, 256 by 256 by 1.
That one's coming 2025.
Okay. Maybe I'll call this the second convolutional stage. So the input channels is going to be 16. Oh shit. There's this crazy ass lightning outside. That kind of scared the shit out of me. Alright. Oh man. It's thundering outside too. If this stream dies, well, hopefully I'll be okay. Okay, how do I increase the number of... how do I upsample? I think I'm going to have to do that with padding. Or I could do the transpose thing. What does the transpose thing do? Okay, so nn.com transpose 2D. So we take the stride minus 2 times padding plus dilation times kernel size plus output padding plus 1. Oh shoot. Okay, yeah, I might ask ChatGPT for this. Alright. Size.
I never thought I'd set foot in the
Oh shit. Okay. Not entirely sure how to do this, but let's just try to work some. Let's try to cook a little bit. So they use the output size. I guess you could force the output size.
order list is piled up. Like, people are not getting their shit because everyone's ordering oats. Honestly, it looks like it's actually big. Did you see like I thought this would be
Okay. Call this down sampling. Call this up sampling. Okay, so we have conj transpose 2D. So we have the same number of input channels as the same number of output channels. We use a kernel of size 3, and we'll just keep the padding the same. Just the default, whatever it is. Okay. Self.conv3. So this is going to be what I want to say is our 1x1 convolution. So we can take the 1x1, do in channels, and then this will be 16, and then we'll take the out channels, and this is just going to be equal to 1. The kernel size is equal to 1x1. Okay. Alright, so forward then. Take the input. I think we might want to flatten this. So I feel like we could do torch.flatten. Take the input. Start dimension is equal to 1. Alright. Let's print. So flattened input is equal to. So flatten input.size. Alright. Also, let me make a text message real quick. Okay. So I would say maybe this is the input layer. And then let's say this is the first convolutional stage. We'll take the flattened input, self dot do conv1. We'll take in the flattened input, so conv1 is equal to, okay. Then let's add, ooh, so they have the idea of max pooling. So pooling, to what I remember, all it really does, I think it limits or reduces the dimension of the convolutional filter or the feature map by aggregating some parts of the feature map. Now, I've kind of forgot exactly what the use is for, so I'm going to come back to that. I think after the convolutional stage, maybe there's an activation we could use. So call maybe relu is equal to self dot maybe f dot relu actually. f dot relu conv1. Okay, take the second convolutional stage. So conv2 is equal to self dot conv2, and then we'll put in relu, and then we'll also just do relu again. So we'll call this relu1, relu2, and then let's do f dot relu, and then we'll put in, let's put in conv2 here. Okay, so one by one convolutional stage. Okay, so this is the final step. We'll take relu2. So I think we'll put output is equal to self dot conv3. Alright, and we put in relu2. And then let's just print let's print all of the sizes here. So it seems like there's people coming out. Let me see. Sit in by cafeteria. Okay. Okay, so we have the flat input dot size. Let's print the relu1 dot size. Relu2 dot size. Then let's do output dot size. Okay, so I think this is going to be pretty helpful. Now for okay. Oh fuck. Model that train. Alright, so this is where we're gonna have to figure out. I wonder how many images there are in this. It's not super clear. Oh shit. Okay. Oh, so this makes sure that all of the inputs are 256 by 256. Okay, so I think there's maybe 168. No. Train images. So there's we'll call this a mystery amounts of validation images. Okay. Okay, so I'm gonna have to leave actually right now to go meet up with some people, but made some good progress here. Figured out kind of a little bit how this might work. Haven't tested out the forward prop, so that's gonna be the next big step to figure out how all this stuff works and be able to set the, I guess you could say, beginning framework. So with that being said, I'll catch you guys in the next one. Peace for now. See ya.